It's my distinct honor and privilege to welcome Professor Shavit as the first keynote speaker of Systor 25. So Professor Shavit received his BSMS degrees from Technion and PhD from the Hebrew University of Jerusalem in 90. He's a co-author of the book, The Art of Multiprocessor Programming, widely called the Bible of Concurrency. He's a recipient of the 2004 Goodale Prize in Theoretical Computer Science for his work on applying tools from algebraic topology to model shared memory computability, and the 2012 Alistarh Prize in Distributed Computing for introducing software transactional memory. For many years, his interests were in multiprocessor algorithms. However, these days he's interested in interpretability of neural computation, understanding the relationship between deep learning and how neural tissue computes, and is part of an effort to do so by extracting connectivity maps of brain, a field which is called connectomics. So, so he's going to talk today about how neural networks might actually think. So over to you, Nir, and please take it away.
Thank you. Thank you for the program committee for having me. And hi, everybody. Good morning. So indeed, I grew up in the systems community, and I appreciate all the, I share values with all the audience. In recent years, I really have moved to actually trying to think about how brains work, and specifically in creating connectivity maps of neural tissue in animals. But then with the advancement of neural network technology, and it became kind of clear that here is an animal that I can just splay right in front of me and look at all its internals. I mean the neural network. And so I moved into this to do work in this area called combinatorial interpretability. And specifically, mechanistic interpretability. Combinatorial interpretability is kind of the take of myself, and my co-authors, Micah, Adler, and Dan Alistarh, of this of an approach to this kind of thing. So let me start by kind of saying what it is that we are looking at. So, mechanistic interpretability is a field interested in really how do neural networks compute. And we do all use neural networks, but if I asked you to say, oh, how does it actually do that? How does it know to answer a question, is that a dog or is that a cat, right? And we care about this, right? We care about this because we're building bigger and bigger AI systems with more and more storage, with more and more compute. And so it is of interest to know what it is that we're building, what it is that's running on our systems. And, in addition to that, of course, there's this whole idea of understanding intelligence. What is it that we do? What is it that, neural networks do that make this kind of phenomena called intelligence appear? And the kind of underlying thesis of the way people think about neural networks today is that neural networks compute using features. Features are kind of functions of the input that that appear during computations. So if I'm looking at a dog, it's a leg, it's a tail, and then I try to understand from the combination of these features, is this a dog or is this a cat? And neural network interpretability is challenging because, we have this phenomena called polysemanticity, okay? And this is that neurons actually, I have a lot fewer neurons than I have in my neural network than I actually have features. I've got probably billions of features in any neural network, and what do I do with them? How do I actually understand what they are, right, when every neuron is participating in the computation of many features at the same time? So this is kind of why it becomes hard. And the people from Anthropic, right, um, have come up with this superposition hypothesis, which essentially says, look, what's happening here is that we've found a way to pack all of these different features into a much kind of smaller um, kind of space, okay, in high dimensional space. And because of that, we are able to actually compute with many, many fewer neurons than we have features. So that's kind of the idea here. And the current state of interpretability, right, is focused on what we call the geometry of activations. Okay, we think of each layer of the neural network as computing, okay, some kind of high dimensional vector. And the people in the space of mechanistic interpretability have been using techniques which some of you may have heard of, sparse autoencoders, transcoders, right, to actually try to look into the neural network, into the activations of the neural network and say, oh, that's Jennifer Aniston there. That neuron is firing for Jennifer Aniston. That neuron is firing for the Golden Gate Bridge, et cetera, et cetera. And this is all beautiful, the idea that we can actually identify which neuron is firing for which feature, right? But there is a gap here. And the gap is that the existing methods, right, don't really explain the logic of the computation. What is the neural network actually doing to get the result? And so this is the subject of this talk. Okay, I'm going to try to give you a little piece of this. And so our goal is going to be to understand the actual logic and mechanics of a neural network. And I think this is the first time that anyone is really trying to do this. So I'll try to kind of tell you the story of how we think you can go about this. So um, so the way we are going to, of course, approach the problem is the usual computer science way. I'm going to simplify it. Okay. So instead of looking at, um, these high dimensional vector spaces, okay, I'm going to think of every parameter of a neural network as being either positive or negative or zero. Okay, I'm going to simplify things. Everything is going to be either positive, negative, or zero. And I'm going to actually look only at the computation of Boolean expressions. Okay? So I'm not going to look at all the possible things that I might do with the inputs of a neural network, but just focus on computing Boolean expressions. And I'm going to try to kind of do that because I think it gives you both a meaningful kind of piece of the computation space, but also because it's going to give me a way to control knowing what it is exactly that I am computing rather than give you a picture of a dog and for you to kind of guess what features the neural networks might be using to detect that this is a dog. Here, we're going to have an exact function, a Boolean function. Okay? So the goal is to explain how features are computed and represented. Cool. So I'm going to start with something really simple. And what I want to do is the following. Here's a neural network I'm going to explain because some of you guys, I'm sure, have not are not that into neural networks and so on. So I'm going to explain slowly what this neural network does. So this is a simple two-layer neural network. Okay. Um, this is the first layer, the weight matrix of the first layer. This is the weight matrix of the second layer. You can see that the first layer has n neurons. Each row is a neuron, and each each column here represents one of the inputs, okay? And so I get an input vector. For example, in this input vector, okay, I have a bunch of variables, x1 through xm, and x1 is 0, x2 is 1, x3 is 0, x4 is 1. And remember, I want to compute Boolean expressions. So I'm going to feed this vector into the neural network. It is going to do a bunch of multiplications. It is going to add a bias and apply a ReLU function, which is a function that takes positive things and and returns the value, and if it's negative, it makes it into 0. Okay, so it's called a nonlinearity. And then after I did this first layer of weights, bias, and ReLU, I will then take the outputs, the n outputs here, and I will apply one more layer, one more neuron that will again do a dot product on this, apply a sigmoid, and get an output. So that's the network. It's a very, very simple neural network. Okay. And imagine that I want to compute a Boolean expression here. And here is my Boolean expression. It has 3 features, right? x3 and x6, x2 and x4, and x7 and x9. Okay? And I want to do this computation. Okay, I want to get an answer to this disjunctive normal form. So, um, so what I'm going to do first is imagine that I'm not going to train this neural network, but I'm actually going to hand code it. Imagine I told you to take this neural network and actually figure out how to compute, this function. Okay? So what would you do? Well, so let's look at this first layer of the network. Okay? So how would I compute x2 and x4? Okay? Well, what we know mathematically is, right, that if I have these inputs, x2 and x4, if I do a ReLU of x2 plus x4 minus 1, that is mathematically equivalent to x2 and x4. Why? Because, if both of them are 1, this will be 1 plus 1 minus 1, and I'll get a 1. The ReLU will return a 1, and it's identical to being both of them being true. And if one of them is 0, then I will get a minus 1 or 0 here. ReLU on that will return 0, and I'll get a 0. So mathematically, these two are equivalent. Okay, great. So I have this exact computation. So now I can implement it in my neural network by picking a neuron, let's say neuron 2, which is this row, and putting a 1 in location 2. I'm sorry about that. 1 in location 2, a 1 in location 4, and everything else will be 0 in this row. And then I will put a bias of minus 1, okay, which is this computation. Now, if I take this vector and I do a dot product along this row, this is what the computation of the neuron is, so I take the vector and I multiply it here, the ones will align, I will get 2 minus 1 is 1, and I'll get an answer. And if one of them was 0, I will get a 0 as an answer. So that's how I code one feature and put it into my neural network. Okay, great. If I have another feature, this time x3 and x6, I will do the same thing, only this time the columns will be 3 and 6. So now I have, a computation of 2 features. And of course, I can continue to do this up to n neurons. Each neuron will compute 1 feature. And that's great. That is what we call monosemantic coding. However, you know, we believe that we have a lot more features in the neural network than we have neurons. So what do you do when the number of features exceeds the number of neurons? Okay? So what we need to do then is what we call feature channel coding. Okay? I need to actually code in different neurons the same feature. So I'm going to spread the computation of a feature across multiple neurons. So for example, to compute x2 and x4, I will actually compute x2 and x4 both here in neuron 2 and in neuron 8. So I'm going to get signal both from here and from here, and this signal is going to be added together to give me the answer, the positive answer, in the next layer. Okay? And I'll do a similar thing for x3 and x6. Again, I have a different set of neurons here, right, that are going to represent it, and I'm going to be able to now get this code, this signal through. But of course, the reason I'm doing this, the reason I'm putting it onto multiple neurons is because as I add more and more features, I'm going to start to have overlaps. And so if I suddenly x7 and x9 is actually coded in 3 different neurons here, right? I might have an overlap with another features computation. So as we see here, right? The codes right? The actual computational channels, pieces of the channel that give me the answer are overlapping here. And when this happens, imagine that this neuron would get, two ones here, then it would compute correctly. Two ones here, it would compute correctly. But in the same way, it would return a one if I had 4 and 7 appear. So it cannot distinguish these two features, even though that's what I really want to do. I want to answer which one of them is it? Is it x2 and x4 or x7 and x9? Okay, so the way we solve this is by having these codes sometimes be overlapping and sometimes be non-overlapping, right? So as long as I have a piece of the code that is not overlapping, even though in some places it overlaps, there will be enough signal that will get through and I will be able to know what the answer is. Okay, so that's kind of the idea of how we are going to compute, features if I had to do this by hand. Okay, so the takeaway here is codes work well as long as they don't overlap with other codes. I'll let you look at this for another second. Okay, so now we can prove a whole bunch of things about these hand codings, okay? And in particular, we can show, right, that if you want to compute the pairwise ands, for example, of m features, you need O of root m log m neurons, and you need O of m square. Sorry, you can use O of root m log m neurons and O of m log square m parameters. So there is a way to code up, up to m features in this way as long as I have enough neurons and enough parameters. And surprisingly, we have an almost tight lower bound on this. And this is a lower bound for any feature, not just ands. In fact, what we can show is that if you will, the number of features that you can have in a neural network that you can compute in a neural network in superposition is essentially linear in the number of parameters. Okay? So think of a neural network. We thought, oh, maybe we have hundreds of millions of neurons and trillions of features. No, that's not true. It's actually linear. Now, this is to distinguish, right, computing in a neural network from just representing the features, which we know how to do, right, in O of log m neurons, right? And so there's a kind of an exponential gap between the amount of, parameters that you need, right, and neurons that you need to compute something in superposition versus just representing the features. Okay, this is for hand coding. But imagine now that I want to actually look at a trained neural network. So I'm going to repeat the exact experiment that I did before. I take my neural network with the two layers, right? The first layer is this one, the second layer is this one, and I'm going to now train it, okay, with a standard training procedure with gradient descent. I'm going to train a network of 16 neurons over features of size 16 with 30,000 random inputs. And I want to learn, okay, a function. Okay, the function that I want to learn in this case is this one. And what I'm showing you here, I just want to go back 1 second. I'm showing you this matrix, the bias vector, and the second layer. This is the outcome of the training of the network. Okay, so I ran 30,000 examples that answered positive and negative on, I gave you an input that had, feature X3 and X11 show up, then, I gave you a positive answer. And if I gave you X3 and X13, it gave you a negative answer. And so I showed it 30,000 examples like this and I trained it. Okay. And what do we see here? So blue is positive, red is negative. These are the weights of the first layer. Okay, this is the bias, and this is the second layer. I just laid it vertically, but it was the same thing that was horizontal before. Okay, so Looking at this, okay, you say to yourself, well, thanks a lot, Nir. That's very informative and great. Thank you. The thing I can deduce is that neuron number 2 is dead. It's not computing in much. Okay, that's what you can kind of deduce from looking at this. Um, but but what I'd like to do now is make a tiny little change. Okay, let's reorder the weight matrix based on the features. So I know what the features are. That's part of the advantage of doing this with a known formula. So I'm going to order them so that x3 and x11 are next to each other, x9 and x13, and so on. So let's just do that for a second. So here is the matrix now. Okay, and what you can see here is x13 and x11 are next to each other. X9 and x3 and x13 are next to x3 and x11 are next to each other, 9 and 13, and so on and so forth. Okay, and if you look closely, you can start to see that something is emerging here. This is not just looking random like it did before. Okay, so let me do one more thing. What I did here is I'm going to take the second layer and I'm going to look only at the positive rows, the neurons that are contributing a positive value to the outcome. Because in the second row, the outputs from here are going to be multiplied by this vector. So this is going to add, this neuron is going to add a positive signal, this one a positive signal, this one a negative signal. I'm just going to look at the ones that give me a positive signal. And here is what the matrix looks like. Okay? The first thing that pops to mind is that, hey, wait a minute. These guys look identical. For every feature that I have, what I see here is that everything looks the same. And this is not Near sitting down and putting these numbers in. This is a network that was trained with gradient descent. What is it doing? Well, if you look at it closely, you'll see that I have positives here and a negative bias, positives here and a negative bias, positives here and a negative bias. Okay, so what we're kind of seeing in the positive rows, right, is that it's actually computing, right, x3 and x11, right, x3 plus x11 minus a bias, okay, not one, but a bias, right? And this is essentially a soft logic computation, right, of x3 and x11. And it's doing it also here and here and here and here. I'm getting a feature channel code. So actually, gradient descent found feature channel coding for X3 and X11. And if I look at, you know, if I look at, you know, X0 and X4, a similar thing appears, right? Here they are, positive, positive, negative bias, positive, 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 negative bias. Here is another set of, you know, a code, right, of representing the features, you know, the feature X0 and X4. And of course, I can look at all of them, right, relative to one another. And I see, for example, that if I look at X3 and X11 and X0 and X4, you see that the coding for this feature overlaps here, but doesn't overlap here. Overlaps here, but doesn't overlap here. So I'm getting this exact property that I hand coded in order to actually compute, you know, the Boolean expression. So what I'm kind of saying is gradient descent did this. It actually learned how to compute, right, these features, right, by employing feature channel coding. It found it. Okay. So this is very exciting for us, discovering this. Um, and and then we kind of looked and said, okay, but what's happening in the negative rows? Because I showed you all this, right? Everything that I showed you here was in the positive rows, the one that have kind of positive contributions. We looked at the negative rows and look what's happening here. What it's doing is, right, for x3 and x11, it's doing x3 and not x11, right? Here it's doing not x3 and x11, it's doing XOR. It's saying, oh, if one appeared and the other didn't appear, then that's a negative example for me, okay? So it's doing positive rows, it's doing a kind of, an and negative rows, it's finding, an XOR. Okay. Um, so we said, okay, let's look at another example. So here's an example of the weight matrix of a vision problem. I give it 128 um, um, pixel input, right? And it's a Boolean input, zeros or ones. And I ask, do I have four ones in a row in this? So it's like a vision problem, but one dimensional. Do I have four in a row? Okay. And I train it with 10,000 inputs over 20 epochs of training, right? And here's the weight matrix, okay, that I get out of this. Again, if you look at this, there's some beautiful, strong things here, mostly kind of, okay, white, and it looks pretty random to me, okay? But now let's do exactly the same trick that we did before, okay? Let's look at the positive rows, okay? The ones that contribute a positive signal in the second layer, okay? If you look at it, what it's doing is it's actually looking for a bunch of things in a row. Look at this. It's doing the equivalent of what I did with the and over multiple locations. So it's doing feature channel coding. And in fact, if I look at it, the average coding row for any set of locations that it detects a 4 in is about 12 or 13, right? And the overlap between features is about 2, okay? And if I look at the negative rows, okay, if I look at why is it not flipping? And if I look at the negative rows, look at this. What it's doing here, right, is XOR. So it's doing, to solve this problem, it's doing exactly what we had expected for it to do. It's solving XOR, sorry, it's solving four in a row by doing an AND of multiple locations. It's looking for an AND of four things, okay? Or an XOR, where one appears and the others, and its neighbor doesn't appear. Okay, cool. So So then we ask, okay, so we have this idea that we have these feature channel codes that represent the features. Okay? The beautiful thing about doing things in such a controlled environment, which this is what we call, combinatorial interpretability. I'm using actually the signs, right, of the locations and not the actual values. I'm not trying to look at vectors in high dimensional space, but actually simplifying it. The beautiful the thing about it is that I can control what the clause is that I'm going to feed in here. Okay, I can tell you what the expression is. It's not a dog and then you train and you try to figure out what the features are. I'm telling you what the features are. Okay, so consider a DNF formula. Okay, with four and clauses. So the clauses are going to be, four ands. Okay, so before I showed you two ands, now I'm going to show you four ands. Okay. And I want to look at, to see what the codes are that are being used here. Because maybe near this whole thing is random and it didn't really, train to do this, but rather it came up with some random thing and it found a way to use it. Okay. So let's try to understand if this is indeed random or the network actually learned the codes. Okay. And so let's do the following, okay? We can look at the patterns. If I'm looking for forands, I can look at a clause, for example, x3 and x11, x9 and x13. Here are the four columns corresponding to it, and I can count how many times I get, for example, four positives, right? Which would be a way to represent the and of these things, or three negatives and one positive, right, which would give me a kind of a no answer, or two positives and two negatives, which would tell me that it's a no, and so on, right? So let's actually run the networks and compute what the frequency of the patterns are, and let's see that if it's random or not. Okay? So the way we are going to do this is, we can take neural networks of different size and we can just um, measure, right, the number of features, sorry, the number of patterns, right, that I have representing a given feature, right, as I increase the number of features. Each feature is a clause, right? So I'm increasing the number of clauses up to 64, and I'm using a network of either 16 neurons, 32 neurons, or 64 neurons. And what happens is what you would expect, right? As I increase the number of features for a network of a given size, the error goes up, right? If I started and all of them, up to 10 features are all coding beautifully for all of the features, the moment I get into the range of about, 16 features, right, you can see, right, 16 clauses here, you can see that the 16 network is starting to develop show a lot of error. The 32 is still doing well up to around 32 clauses, and boom, here it is. Now it's starting to deteriorate, and 64, right, continues to go. So we see that, okay, as I increase the number of clauses, as I increase each clause being a feature, I increase the number of features. Clearly, a network of a given size starts to collapse in performance. Okay, let's pick the 32 neuron network with, four and clauses and see what happens for it. Okay, so what I'm showing you here are two graphs. Okay, this is a graph of the positive rows. Okay, and what I'm doing is, just as before, I'm increasing the number of features along the x-axis, and I'm looking to see how many of each code appear to represent a clause. How many of these, either 4p's or 3n 1p's or 4 negatives or 3p 1 negatives appear. And what I see is the following phenomenon. Okay, I see that 4p, right, doing a kind of an and of 4 by having four positives, right, um, actually, you know, appears, here, like for example, when I'm doing doing one feature, right? So when I do one feature, I can see that I'm coding it with about 7.5 or 7 on average, seven, let's say a little bit over 7 on average. And as I increase the number of features, naturally, the number of codes, right? The number of these patterns that I can have, 4p patterns per clause, goes down, right? And this corresponds exactly to the loss of accuracy, right, that we saw. So it's deteriorating. And look at this. While this is kind of going down all the time as accuracy goes, down as I get more and more error, right? If you look at the other appearance of other kind of patterns, what you can see is, right, that, they're actually getting to be, there were very few of them in the beginning, right? And now they're kind of adjusting to be where they were when things were random. So on the right side, right, on this side, what you can see is what would happen if I just looked at the prevalence of these codes if I just had randomly flipped coins to get them. What you can see is, right, that if I look at this pattern, the 4p pattern, right, it would appear on average once um, per feature, once per clause. But what I'm seeing here is that it's doing it, 7 times per clause. So clearly not chance. Okay. And if I actually change it, right, instead of for and, okay, of just positive variables, I do, for example, a for and where one of the variables is negative, then look at what happens. The 4p is just flat here, but the one that corresponds to 3p and 1 negative in the clause, where the negative value is in the clause, that pattern appears to look just like the 4p did before. It actually found this code, and it is the one that it is kind of, using in a non-random form, because if it was random, this is the prevalence that I would have. Okay. So it's not random, okay? So what can we do with this? Well, one thing we can try to do is explain scaling laws. And I'm sure some of you have heard of scaling laws of neural networks, and people kind of put a lot of, they have, models of increasing size. And with this model, the models of increasing size, they kind of train with more and more data, and they kind of add more and more features. And we kind of see typically that as I increase the model size, right, the error goes down. This is the scaling law for neural networks, right? As I increase the number of, the number of neurons or the number of parameters, the error, the training and the test error goes down. That's all known. But imagine now that in my experiment, I know exactly what the expression is, what it is that I'm computing in terms of features. So I have 64 feature DNF with four ands, okay? What am I going to see? Well, if I count now the 4p positive patterns and the 3 and 1p negative patterns, right? What I see is that what actually is happening is that the 4p patterns increase, right? The coding per feature goes up. And it's about 7 here when the error is 0. And it's about 18 here. Okay, so much more than random. And that kind of explains why it is that larger and larger neural networks can actually, reduce the error. It's because I'm able to actually code, okay, do feature channel coding better. Okay, so we have an explanation in this very kind of limited setting, but still an explanation of what scaling laws might look like. Now, of course, I just want to say before we continue, great, Nir, you're saying you explain scaling laws. We have to remember this is science. I'm doing this on a very small example, right? This is I didn't do it on ChatGPT 5, so this doesn't necessarily have implications for ChatGPT 5, but it is a hint in this very small setting, right, that you can actually analyze all kinds of phenomena that happen in neural networks and try to get understandings in this very limited setting. Okay? And, this is a kind of way that we've always done science. Not to compare, right? But Mendel, did, kind of genetics on peas, not on people. But we believe there's a relationship. And, in the same way, we hope that these things have meaning for bigger neural networks, but we don't know yet. So we kind of want the community to look at this and see, oh, can we use these techniques to actually understand all kinds of phenomena in neural networks? Okay, so how does gradient descent actually find these patterns? Okay, so let's look at an execution, okay, of a DNF of four and clauses over 32 variables, okay? And what I want to do is I want to look at the hidden layer and see what happens as I train it with 20 epochs. So here is my neural network. This is the second layer. This is the first layer. And I randomly flipped an initial state here. Okay, so you can see positives and negatives at about an even distribution. And here in the second layer, it's the same thing. I ordered them with the positive rows here and the negative rows here. And this is my starting state. I start training. And after 3/5 of an epoch, I start to see if I ordered, by the way, the x-axis is again ordered by the features. You can see that there are 4p patterns appearing in the positive, and you can see 3 negatives and 1 positive appearing in the negative, even after 3/5 of an epoch of training. And then I go on and train a little bit more. Now I'm at 6/5 of an epoch. You can see clearly appearing 4 positives. So gradient descent is quickly finding these 4 positives all over the place. And then if I keep on going, now I'm at 2 epochs. You can see them even more clearly. 15 epochs and the final set of values. What you can see here is feature channel coding. Look at this. A set of codes here, and a set of codes here. Sometimes they overlap and sometimes they don't. Okay? So kind of a fascinating phenomenon that's happening here, that we can look at the neural network as it trains and understand how the features emerge because we can track the codes. And in fact, I can do this. I can look at the codes and graph them. Here are the 20 epochs of training. So 100 over 5 is 20. So I've got my 20 epochs of training. Okay, and this is not a linear scale here. I kind of, this is up to 3 epochs, and then I sped it up a little bit here. But what you can see is that as I start training the network, I'm going to track how many I have of each one of the patterns. So as this is the error, and you can see that it kind of goes down to zero, close to zero. And you can see that as the neural network starts, right, after, you know, um, after an initialization um, phase, right? What you can see is that, not surprisingly, the pattern 4p, 4 positives, starts where we would expect randomly, right? In the random distribution, the expectation of having 4 positives is about one pattern per feature, per clause. And look at this. As I start training, 4 positive starts to shoot up, shoot up. Everything else is going down, but it's shooting up, shooting up, shooting up, shooting up until it plateaus here. So at about 9/5, epochs, I have coded with 4Ps and I've saturated this, but the error, there's still error. And then what happens? Then what happens is that I've got the 3 negatives, the 2 positives and 2 negatives that are being flipped. One of the bits here is being flipped to 3 negative 1 positive. And when I finish doing that, I get my zero error. So it coded, okay, gradient descent, quickly found 4 positive codes, and then after that kept on flipping, in the negative until it got zero error. We can use this approach to understand how, training actually finds features and how it codes them. So great. So I want to finish by kind of thinking about, okay, so how do we take this to bigger neural networks? Okay, so for this we need to do something a little bit different. And the reason for this is because in an actual neural network, the inputs, right, are not one to one, with the width of the neurons, right? They're actually look a little bit different. And so let me show you what this might look like. So here's a kind of a way we want to model the computation of a neural network. Okay, so people think of a neural network as what we call a feature circuit. Okay, I've got my input features, from 1 to M0, and the first layer of a feature circuit takes these features and computes a new set of features, M1, that are dependent on these ones. There are functions of these initial features. So first layer of the network takes the input features and then transforms them into a first set of first layer features, right? And remember, the numbers here, the size of this so-called matrix that I have here to represent this is M1 by M0. It's very big. This is the number of features, not the actual number of neurons. And the second layer takes these features that are the output here, computes a new set of features, and so on and so forth, until I get the last set of features, which I can compute some function on and get an answer. So this is the abstract feature circuit. In the real world, the neural network actually does the following. It takes the features, it embeds them, it reduces them to N0, the number of neurons that I have. Okay? Right? A much smaller space. Okay? That is a function of number of neurons, the size of the rows actually of the neural network, right? So do an embedding, then um, you have your first weight matrix, right? Your neural network's weight matrix, right? Which is N0 by N1, where N1 is the number of neurons here, right? And N is much smaller than M, right? Apply a Rayleigh bias, then the second layer, N1 goes to N2, and Rayleigh bias, and so on. Finally, I do a softmax and I get my answer. Okay? So, so great. So then if if this is the way the actual neural network computes, it's actually computing in what we call superposition, right? It's computing a circuit that is much, much bigger than it, right? Using an actual number of weights and neurons that is much smaller than it. Okay? And we already said, right, that this is the beauty of the neural network, that it actually can do this. It can compute in a superposed way. Okay? So how do we represent this computation? Well, we can think of this computation in what we call a disentangled view. Okay? In the disentangled view, I can think of, I have my initial embedding, okay? Call it C0, okay? And what C0 does, okay, is compresses the input features into a smaller space. And then I can think of the first weight matrix as actually a multiplication of two matrices, a decode matrix and another compression or coding matrix, okay? The decode matrix is M0 features by N kind of, in internal neuronal representation here. And then I take, um, you know, um, um, M0 and multiply it by N1. If I actually multiply these two matrices, I would get W1. So I'm kind of representing W1 using two matrices that if I multiplied them out, I would get exactly this matrix. But this opened up matrix, what I have here, right, the thing that the size of this is the number of features in the original input. Okay? And so I think of the neural network as I got the features, I compress them, then in every layer I decompress it, decode it, and then I compress it back. And when I compress it back, I do the computation that I showed you. C1 here is the matrix with the codes that I talked about before. Okay? And in the next layer, I do the same thing. I decompress and compress again. Every one of these C's is the kind of matrix with codes that I showed you before. And I keep going like this. And that's kind of a way of thinking about how these, real neural networks represent this abstract computation. Okay. So if I think about it this way, okay, I can do what we call cascading feature disentanglement. That's the way that I want to actually disentangle very large neural networks, okay? And the way we want to do it is the following. We want to use the compression matrix, the values in the compression matrix, and the values in the weight matrix in order to decode what the the weight matrix, to see what the actual coding looks like. So I can keep on doing that, and if I got the C from here, I can use it with this one to get the next one, and so on and so forth. Now, um, let me just show you a very simple example of this, because what I said might seem far away from everything that I've talked about before. But let me just kind of show you what I mean. Here is the first layer. I compressed to size N0, then I did, a D and a C. Okay, so my weight matrix, W1, right, represents essentially D times C. Imagine that D was the identity. It was the identity in all of the examples that I showed you before. Then, because D is the identity, there's no embedding, and D is the identity, right? Or the embedding is the identity, and this is the identity, right? Then what I get is a raw matrix where I see the feature channel codes. Okay? And the compression matrix, the hidden one, right, which is could actually be gotten by multiplying the weight matrix times the compression. Why? Okay, because if this is embedding it and this is undoing the embedding, it's the inverse of the embedding, then multiplying this, I'm sorry, multiplying C0 by the weight matrix will give me C1. So this is what C1 looks like. Imagine now that C0 is not the identity, but a Hadamard matrix, for example, a Hadamard embedding. So if I train a neural network where I embed the inputs with a Hadamard embedding, and then I train the neural network, this is what W1 will look like in the entangled space. This is what usually you see in the weights of a neural network when you look at it. It looks like mumbo jumbo. Okay? It's hard to tell the relationship between anything. And the reason is because this is entangled space. Okay? And so if I actually want to see the coding matrix, not W1, but the actual matrix that holds the codes, the feature channel coding, I multiply C0 by W1, and the result is this. This is C1. You can see the feature channel codes in it. Okay? So I can actually do this disentanglement. Now, in this case, it's easy because I don't have a ReLU here between the two, but it's fascinating because, I mean, you can do this even with a random embedding. Here's a random embedding, okay? Here is what the weight matrix looks like, okay? And I multiply this by this and I get the features that are hidden in there. I can see them. Look at this. XOR's here, AND's here, that's what it's doing. Okay. So the idea is that I can use this kind of disentanglement approach to unravel, the actual coding that happens in very large matrices. Now, we're not going to do this, I'm oversimplifying here. You actually need to use, autoencoders and do a whole bunch of technology to do this, but this is the research that we are doing right now, trying to actually apply this approach to much larger networks so that we can understand what the coding is that they're doing. So to summarize, the work that we've been doing, right? Combinatorial interpretability, right, is a kind of a simplification of neural network computation by looking at not changing the actual computation, by changing the way we look at it. Okay? And we're not going to look at activations, but actually at the weight matrices. So we want to understand what is being computed, right? Not by trying to relate inputs to outputs of the network, but by actually looking at this beautiful weight matrix that we have here, right? This is, for me, it's very exciting because, right, we try to understand how brains of animals work. I've been working on this for a while, right, by looking at the neurons and the connectivity between them. Here I have an actual connectivity map in the weight matrices, and I can look at it and I can try to understand what is actually going on here. And we have a hypothesis, the feature channel coding hypothesis, which is how we think neural networks are actually doing this computation, right? And we have a playground, right? A sandbox that we can actually try to do experiments to explain things, like scaling laws and so on and so forth, maybe sparsity. We have results for sparsity, for other things. We can explain these phenomena, okay, in our limited setting, but maybe also find ways to expand them to very large neural networks. Um, This will allow us, of course, if we can understand things, we can improve the training, the safety, and so on, and hopefully this will have a big implication on neural network computation. And of course, this brings me back to the place that interests me, is that maybe we can take the same techniques and apply them to actual, neural tissue. And understand how we and maybe start with mice, but how we actually think and how our computation proceeds. Thank you.
So thank you, Nur. We have time for, I guess, a couple of questions. And I'm looking at the Slack channel. Nothing has appeared yet. So while we wait, maybe I'll start with a question for myself. So in the hypothesis that you derived, you assume stochastic gradient, right, as the underlying algorithm for
Yes.
training. And I wonder if we change the algorithm to something else, I don't know, Bayesian-Hoppin or Monte Carlo or something, will that change the hypothesis, or can you comment on the relationship between the two?
So if it, my guess is that if it actually trained, right, then it's finding some form of feature channel coding. And maybe if you use gradient descent, it finds you one. But if you use another approach, it finds you another. But I still think that in the end, it actually is going to be using some form of channel coding. And this is really kind of consistent with the superposition hypothesis that people believe in the interpretability space, right? Which says that essentially what enables me to compute is that I have, these kind of vectors that are kind of, close to orthogonal in an activation space, right? So feature channel coding is just an actually exact way of doing this, right? So that you can actually count the patterns and understand what they are. But in the larger context, I think this is completely consistent with what people are observing with all the other methods that they've used for training neural networks.
Interesting.
Yeah. Yeah.
All right. Other questions?
There is a question in the Slack channel.
Right. So this question is about, can you comment on how this can lead to quantifying the quality of learning?
The quality of learning.
Right. Oh, I'm sorry.
So
Quantifying the learning quality.
I'm not sure that I understand what that
Right.
means. You mean the error, the how much error you have? You can actually relate directly the um, the amount of coding with the error. And in fact, you can actually run executions. You can actually look at the execution with the codes that you have and see how the codes are being computed in execution time and see that actually what it's doing, right, what the network is doing is actually doing ReLU of this and this and this minus bias. It actually does that. And so the moment you play around a little bit with the bias or with one of the variables, you start to get a little bit of error, right? And you can actually quantify this. So the answer is you can get a real quantification of what the error will be if you make a small change in the coding that you have.
All right. I've got one more question, which is, so in live animals, the neurons are not laid out in nice matrices. So is there any information encoded in the distance or position between the neurons that may be lost by applying a matrix representation?
Yeah, this is a really fascinating question that people, of course, think about. Um, Distance matters in terms of um, the distance in a given neuron matters, and the distances between neurons matter in terms of timing. But my belief, and this is just me, this is not all researchers in connectomics, right? Um, I believe that as the network, as the neural tissue is trained, we actually train it to be, um, I will call this synchronized, so that the arrival of messages on neurons, even if they are far away, are synchronized, so that when you get inputs to a given dendrite of a neuron, then the arrival times are actually, the network was pruned to make it so that they arrive synchronously. Okay.
Mm,
And that means that the matrix representation is probably a very good simplification of this, even though it doesn't take distances into account. Now, of course, I could be wrong, but it just seems like this is a phenomena that we do see. And so my guess would be that as a first cut, a matrix-based representation of the connectivity map is a good one. And in fact, in connectomics, this is one of the standard ways in which people actually try to represent, the connectivity maps of animals.
Okay. Nir, thank you very much. It was very insightful.